Welcome back to Integral Calculus. In this video, I want to talk about infinite series. An infinite series is a concept that has come up at least once before in your study of calculus. We use infinite series in the definition of the integral, although because it's kind of something that we talk about briefly and then never use again, you probably didn't hear the vocabulary of it, and you really didn't do any work with infinite series at the time. The goal of this video is to put all of those ideas onto a sound theoretical footing so that we can build on it and use it for more powerful techniques that are yet to come. But the idea is going to start with a summation. We've defined a summation previously. Again, you've used a summation previously, although not in a lot of detail and not often. We can now be a little bit more formal and start by defining A as a sequence, and then we can define the summation. The sum, k goes from 1 to n of ak, is equal to a1 plus a2 plus ... plus an. I'm sorry, that should be a capital N. There we go. I need to be consistent about that. One of the things that is going to drive me crazy as the instructor, and so it's something that you need to pay attention to as well. I'm going to use capital N, I'm going to use lowercase n, and I'm going to use k at different points for talking about integer variables. I'm going to have specific meanings for each of them because they're all going to exist in the same equations, in the same formulas, so paying attention to which one is going where can be a challenge. And it can be a challenge for me as well because there's a lot going on and a lot to keep track of. So this idea of summation is something that you have seen before. And we know if we want to evaluate, say, something like the sum k goes from 1 to 5 of 2k plus 1, well, we're going to get 2 times 1 plus 1 plus 2 times 2 plus 1, 2 times 3 plus 1, 2 times 4 plus 1. I'm running out of space over here, but we'll also have 2 times 5 plus 1. Right? So that's 3 plus 5 plus 7 plus 9 plus 11. And when you add all of those together, you should get 35. Yeah, 35. But in this lesson, I want to try to put the idea of a summation on a little bit of a more firm theoretical footing. I'm going to define a summation as a sequence. Specifically, we're going to call this the sequence of partial sums. So I'm going to define a new thing, S sub n, as the sum, k goes from 1 to little n, of ak. All right, so again, pay attention here. N is the index for my sequence of partial sums S. And then k is my index for the sequence I am summing together. I've got two sequences going on. They're indexed using different letters because there is a relationship between them, but it's not really a necessarily clear one. So writing out the first couple of terms, S1 is just going to be A1, S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3, and so on. Perhaps a somewhat easier to work with definition is to define my sequence of partial sums recursively. So I will define S1 equals A1, that's part of my definition. And then my general term is going to be Sn is equal to the previous term, Sn minus 1, plus the next term in the sequence being summed, An. So if you think about this, right, let's take S3 as an example. You've got A1 plus A2. That's exactly the same thing that you had as S2. So we take A1 plus A2, we replace it with S2, and then we add A3. Right? So when n is equal to 3, n minus 1 is equal to 2, this is S2, and then this is S3. So it's a recursive definition for the sequence of partial sums, and that gives us a footing in which to start trying to talk about how this sequence is going to work. Because I don't want to just stop somewhere along in the sequence. What I'm looking for, the title of this video, the infinite series for the sequence AK is denoted as the sum k goes from 1 to infinity of AK, and it's defined as the limit as n goes to infinity of Sn. Right? You've used this definition, this idea of a summation that goes to infinity and turning it into a limit as part of the definition of the definite integral, although you probably don't even remember that that's a thing that you did. So as a relatively simple example, let's consider AK equals 1 over 2 to the k power. We can list out the first couple of terms here. This sequence actually works really nicely starting at k equals 0. So I'll go ahead and start at 0 on this one. So 1 over 2 to the 0 is 1. 1 over 2 to the first is 1/2. Then we have 1/4, 1/8, 1/16, and so on. I think that it's pretty obvious that this sequence is going to tend to 0. And that's actually kind of important for this process. If you are dealing with a sequence that converges to 0, you can have an infinite series. Not guaranteed, but it's possible. If you have a sequence that does not converge to 0, either it converges somewhere else or it doesn't converge at all, you have no hope on the infinite series that you're building off of it. But now that we have a little bit of our original sequence defined, let's go ahead and start thinking about the sequence of partial sums. We've got S0, which is 1. We've got S1, which is 1 plus 1/2. Well, that's 3 over 2. We've got S2, which is 1 plus 1/2 plus 1/4. All told, that's 7/4. We've got S3, which is 1 plus 1/2 plus 1/4 plus 1/8. All right, well, that's 15/8. And let's go ahead and list out one more. S4 is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. That turns out as 31/16. There is a pattern to these numbers. And in trying to do calculus, identifying patterns can be dangerous because there are a lot of patterns that deceive you. But in this case, it's actually a pattern that will hold out. For each of these values, if you take the last term in the summation and you add it to what you have, you're going to get 2. Right? 1 plus 1 is 2. 1/2 plus 3/2 is 4/2, which is 2. 1/4 plus 7/4 is 8/4, which is 2, and so on. So with that pattern, we can come up with a closed form representation of this sequence. Sn is going to be 2 minus 1 over n squared. I'm sorry. 1 over 2 to the n. Pay attention to what I'm doing. Right? In the second case, it was 1 over 4. 2 squared is 4. In the third case, it was 1 over 8. 2 to the third is 8. In the fourth case, it was an extra 1 over 16. Right? 4 squared is 16. If you try to take the limit on this thing as n goes to infinity, you'll have 2, which stays alone. And then you'll have a 1 over infinity term. 1 over infinity tends to 0. So the limit in this case is 2. The sequence converges to 0. The sequence of partial sums converges to 2. And because the sequence of partial sums converges, we can write that as the sum k goes from 0 to infinity of, I'll write it out, 1 over 2 to the k is equal to 2. Equal signs and infinity can be very confusing, and you always have to be cautious around them. But in this case, that is the notation that is most common. Let's compare that result to what at first glance might seem like an even simpler series to work with. We want the sum k goes from 1 to infinity of 1 over k. This is sometimes called the harmonic series. It has some very useful properties or very useful applications to the properties of sound and music. But for right now, let's just think about, well, 1 over k itself. If we start listing that out, that's 1, 1/2, 1/3, 1/4, 1/5, and so on. And so our sequence of partial sums, S1 is going to be 1, S2 is going to be 1 plus 1/2, which is 3/2. Although I actually think this one's going to be easier if I start listing things out as decimals. So 1.5, S3, 1 plus 1/2 plus 1/3. comes out at something like 1.83. S4 will be 1 plus 1/2 plus 1/3 plus 1/4. That's going to come out at something like 2.08. S5 is going to come out at 2.28, and so on. Unlike the last example, there is no clear pattern here. Right? We don't have that we're getting closer to 2 and we're making that step, but we're still coming up this much short, and we're coming up the same amount short every time. In fact, we just keep growing and growing. This series diverges. So even though when you take the limit on the original sequence that we're summing up, you get 0. That's not enough. It is necessary but not sufficient for the sequence to converge to 0 in order for the series to converge at all. If the sequence does not converge, the series will not converge. If the sequence does converge, the series might diverge, but it's not a guarantee. There's always the possibility that something weird is going to go wrong. Right? I know that this particular illustration is not very satisfying, but hopefully it gives you a little bit of something to play around with. If you try plotting out the next couple of numbers and continue to see how this goes, you are going to see that this series is going to continue to grow, and it will just continue to grow forever. The harmonic series is interesting mathematically because it kind of falls on the knife's edge. A series that grows any slight bit slower than the harmonic series will converge. There is a classic example in higher level mathematics. It goes in higher level math because proving it is painfully annoying. Not difficult, but annoying. If you take the harmonic series and you eliminate all of the terms where a 9 appears in the denominator. So we keep 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. We skip 1/9 and we go straight to 1/10, 11th through 1/18, skip 1/19, continue on to 1/20, and so on. That slight modification is enough to make the harmonic series converge. But knowing that this is a divergent series is a useful fact to have in your back pocket. There is a lot more we can do with series, but for right now, I'm going to end with one for you to look at. I know I haven't done the example myself, but this video is getting long, and the previous video was a lot longer than I would have liked it to be. But I would like you to take a look at the sum, k goes from 1 to infinity, of 1 minus 2 to the k, and I would like you to show that this series diverges. I didn't go through an example of showing this, but using the facts, using the ideas that I've discussed in this video, you should be able to do this on your own. Take a couple of minutes, see where you can get to with that, and I'll see you in the next video.